All right, so welcome to Math 349, Operations of Order. So this is lecture 27, and this is, I think, the fourth and the final lecture on gaps. And so that means, I'm open to new topics for Monday. So if there are things you want me to talk about related either to the chapter that you're working on or the math outreach project, let me know, and I will work that out. All right, so I'm assuming at this point that everybody is comfortable with the notation to talk about decompositions of numbers so that we can then start talking about gaps between summits. And really, the reason this is so interesting is we're trying to figure out what is the waiting time between events. There's an entire theory developed, devoted to problems like this. We're trying to start off with something very simple. So the very first thing we looked at was spacings between integers. That wasn't exciting. It was too simple. Spacings between polynomials. We could write down an explicit formula for what the gaps would be. We then talked a little bit about primes, and then all of a sudden at primes, things are getting a lot harder. And so frequently what happens is rather than trying to prove something about a specific instance, you talk about what happens on average. And ideally, you have the smallest possible family. The more you average over, the easier the problem is, but the less likely you are to see something interesting because the interesting stuff has been washed away. So we want to look at the smallest possible families, bless you, as we can. Bless you. So what we'll start off with is binary expansions. And so when we're looking at binary expansions, let's say I give you, some number n, and I write it maybe as something like this. And the 2 means it's in binary. So over here, if I write down the index, this would be index 0. Oh, maybe use a different color. So here's the index. And this would be 0, 1, 2, 3, 4, 5, 6, 7, 8. And here, we could write n as 1 times 2 to the 8 plus 1 times 2 to the 7 plus 1 times 2 to the, is it 5th? Or is it 4th? I think it's the 4th. 4th, to the 4th, plus 1 times 2 cubed, plus 1 times 2 squared, plus 1 times 2 to the 0. So now notice that the number of summons is going to be 6. So I could write this as the sum, k goes from 1 to 6 of 1 times 2, and then I have to choose how I want to write my power. And maybe I'll write it, n sub k. Or I could write this as the sum, k goes from 1 to 6 of 1 times b sub nk. And here, n1 is going to be 0, n2 is going to be 2, and 3 is going to be 3, and 4 is going to be 4, and 5 is going to be 7, and then the last one, n6, is going to be 8. So you give me a number, I can tell you what indices there are. And if I wanted to look at gaps, the gaps wouldn't be that hard. So what would the gaps be? It would be n2 minus n1, n3 minus n2, ... all the way down to n8 minus n7. So what are our gaps going to be here? Two, then 1, and then another 1, and then a 3, and then a 1.
Why do we go 1 times 2 the n sub k? Why is that 1 times b sub n?
So here, your b sub m is going to, let's do this. I'll change this number to an m. And we'll say b sub n is 2 to the n. Those are the terms in my sequence. So the sequence of the b n's is just going to be 1, 2, 4, ...
And then you say we have n1 equals 0 and n2
Right.
Is that
It's
the index?
it's which terms do we have? So if you look at these and try to see which indices arise in the decomposition.
So what can you point to N2?
So N2 would be the second term. It would be over here. That's the second one we have.
Oh,
This is the first one. We have 2 to the 0. We don't have a 2 to the 1. The second term we have is a 2 squared. The third is a 2 cubed. The fourth is 2 to the 4th. The fifth is 2 to the 7th.
so N1, you're saying equals x, like N2 equals 2 is the exponent?
Yes, it's telling us which b term do we have. So what you have to be a little bit careful about is this. It's convenient to index the b's starting with 0, because we want to have 1, 2, 4, 8, 16, and so on. And so it's convenient to just start with the 0th index. For a lot of sequences, we start off with the first index is 1. Here, in some sense, the first index is 0. If you want to, I could have started off with N0. I could have had a sum going from 0 to 5. If I go from 1 to 6, then this is telling me how many summons do I have. I have 6 summons. If I go from 0 to 5, that's not including, the 5 would not be the number of summons. It would be off by 1. This is not a big deal. It's a small notational issue in terms of how we're counting, but it's important that everybody understands where we are. So if you are not clear, you have to speak up. I just have my number and I'm just representing it. I only care about which terms actually arise. Do I use 2 to the 0? Do I use 2 to the 1? Do I use 2 to the 2? Do I use, etc.? I use 2 to the 0. So that's why I'm going to have a 1 here. I don't use 2 to the 1, so I'm not going to have a 1 there. So I could write this as this is just going to equal 2 to the 0 plus 2 to the 2 plus 2 to the 3 plus 2 to the 4 plus 2 to the 7 plus 2 to the 8. Or I could go in the other way. I could start with the largest one and go down. It doesn't really matter which way I do it. These are all different ways of writing my number. And it's just which terms actually arise. Because I'm doing a binary expansion, things are nice. The only possible coefficients is 0 or 1. If I were to do base 10, then the coefficients would be more complicated. I could have 0, 1, 2, all the way up to 9. And then when I start looking at gaps, I could have gaps of length 0, because I could have several copies. If I have 10 squared, which is 100, if I'm writing the number 2023, I don't use any hundreds, but I would use 2 tens. So if I were to decompose 2023, it would be 1,000 plus 1,000 plus 10 plus 10 plus 1 plus 1 plus 1. So it would have multiple gaps of length 0. Here, I'm not going to have any gaps of length 0 because I can't have any repeated summons. This is very similar to the Zeckendorf decomposition. The difference between this and the Zeckendorf decomposition is for the Zeckendorf, we can't have 2 adjacent summons being taken. So this would be illegal because I have 8 and 7. It would be illegal because I have 4 and 3. It would be illegal because I have 3 and 2. And then once you know which indices you have, the question is, how long do you have to wait from one index till you get to the next index in your decomposition? And so when I have my sequence, I just need to see which terms do I actually choose. And so the first term I choose is the 0th, then I choose the second, then I choose the third. So I want to make sure everybody understands this. Is this clear, or do you still have a question? If you have a question, please speak up. You're almost surely not the only person who has a question. You'd just be the only person brave enough.
Yeah, I just want to confirm. So I see why we have N1 through 6. Is there 6 summons?
The 6 summons.
So N1 equaling 0.
That just means the first summon is B0.
Because of the fact that it's 1 times 2 0. That's the exponent, correct?
Yes. And the next one that we have is 2 squared. So this is the 0th term of the sequence. This is the second term of the sequence. There's just a small shift because of how we're defining things.
And then the gap is
the gap is just the distance between summons. Is how long do you have to go from one summon to another? But I don't mean by the numbers. Because if I did the numbers, if I'm going from 2 to the 3 to 2 to the 4th, that's a gap of size 8. And if I go from 2 squared to 2 cubed, that's a gap of size 4. So the physical distance between the summands is large. The gap is just by the index. So this is the difference between adjacent indices. So I don't want to say going from the 2nd to the 3rd summand is a lot less than going from the 3rd to the 4th summand. It's both. I've just moved my index up by 1. They're both the same walk further. I'm walking along the B's, and as I walk along the B's, I stop and say, do I take you or not? And so I would have 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, 2 to the 7. And as I walk down, I have here, I don't have here, I have here, I have here, I have here, I don't have here, I don't have here, I have here, oops, and I had 2 to the 8. And I have here. So as I'm walking down, I'm just seeing which summons do I take. So I'm going to have, in my decomposition, I'm going to have B0, I'm going to have B2, I'm going to have B3, I'm going to have B4, I'm going to have B7, I'm going to have B8.
I don't know, you skip 1, 5.
Well, because I'm choosing a specific number. I'm choosing the number 1100111101 base 2. So I'm giving you a specific number. You have to look at all possible. Each number is going to have its own binary expansion. Yeah. And once I give you its expansion, you can then figure out what your gaps are. Does this? So if I give you any number, it's not that hard to find the gaps. So, given some number, say epsilon n minus 1 dot 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 epsilon 1 epsilon 0 base 2, can find gaps. Look at differences between epsilons that equal 1. So for example, if I have epsilon 8, which is 1, I have epsilon 3 equals 1, and then epsilon 7 equals epsilon 6 equals epsilon 5 equals epsilon 4 equals 0. What's my gap? So what would the gap be in this situation? I'm sorry? It would just be 5. I have to move 5 indices before I get to the next index, which is not 0. I have a desert of 4 zeros, and so it takes me 5 units of walking before I get to the next one. Is this clear? Okay, so now what we want to do is let's consider all m in some interval, let's say bn to bn plus 1. So that would be 2 to the n, 2 to the n plus 1. How often do we have a gap of length g? That's the question we want to solve. Now, if we're in this interval, we know we have to have 2 to the n as one of our summands. So we know we can write m as 2 to the n plus, and then it'll be a sum. Let's say j goes from 0 to n minus 1, epsilon j 2 to the j. We know 2 to the n is a summand, as in the interval 2 to the n, 2 to the n plus 1. But we don't know about the other terms. And depending on what number I give you, some of the epsilons will be 1, some of the epsilons will be 0, or maybe I give you the number 2 to the n, in which case every other epsilon is 0. Or maybe I give you 1 less than 2 to the n plus 1, in which case every epsilon is 1. So for each m, you can look at its decomposition. For each m, you can look at its gaps. And then what you can do is you can average over all the numbers. And there's a couple of ways you can average. So some numbers have more gaps than others. So how would you have more gaps than others? What would have to be true to have more gaps than another number?
Larger.
No, they don't have to be larger.
It would have to be some, so the closer it does become.
Well, the more summons you have, the more gaps you have.
If you want the biggest gap possible, and are you saying? Like
Well, no. If you want a very large gap, you would want to have few summons. But if you want to have a lot of gaps, the more summons you have, the more gaps you have. The number of gaps is one less than the number of summons. So just because my number is larger doesn't mean it has more gaps. I could choose a number that is very large, for example, 2 to the n plus 2 to the n minus 1 versus 2 to the n plus 2 to the n over 100 plus 2 to the n over 100 minus 1 plus ... plus 2 plus 1. This second number has a lot of gaps. This has only one gap, but it's larger. So just because you're larger doesn't mean you have more gaps. This number is tremendously larger. If you look at 2 to the n over 100 versus 2 to the n minus 1, 2 to the n is much, much larger than 2 to the n over 100. That said, both of these numbers are still, however, on the order of 2 to the n. And so it's useful to be looking at numbers that are roughly of comparable size. If I look at a number of size 100 and I look at another number of size 10 to the 100, I would expect them to have different properties because your number of size 10 to the 100 is so huge. Most numbers, maybe it's not unreasonable to think half of your epsilons are 1, half of your epsilons are 0. So if I give you a number of size 2 to the 100, you would expect to have a large number of summons relative to a number that's just of the size 100.
Is half the numbers of epsilon.
Well, we could actually have all the epsilons be 1.
Wouldn't that be 0 yet?
No, if all the epsilons are 1, all the gaps would just be 1. How long do you have to walk? What do you have to add to get to the next index? So if you go back, to get from the second to the third, I have to add 1. It's a gap of length 1. You want to count it like that because if you decided that that's a gap of length 0, then what would happen if you had a repeated summand? You want to allow the repeated summand to be a gap of length 0. You don't have to move before you see the next copy of that index. Is it still clear or no?
The maximum number of gaps is if you got a binary representation of just alternating pairs and ones.
The maximum number of gaps would be as if every epsilon is 1. The number of gaps is 1 less than the number of summons. The gap is how long do you have to go from one summon to the next? How much do the indices have to increase by? So the more summons you have, the more gaps you have. And so if we only have a few summons, then we're not going to have that many gaps. So in fact, if I just give you the number 2 to the n, then there'd be no gaps. If I give you the number 2 to the n. If I give you 2 to the n plus 2 to the n minus 1, there's 1 gap. And they're adjacent in terms of if you look at their indices. Physically, the numbers are very far apart. But if I'm looking, how long does it take to get from one index to the next? I only have to increase by 1. So the gap would just be 1.
If there's 2 and Well, it's 2n minus 2, still have one gap, but the gap would be of size.
Then the gap would be of size 2, exactly. Let me just make sure. Right, so if it was 2n plus 2n minus 2, it would be one gap of length 2.
So you can only have
Gaps are integers, gaps are integers.
but the length can be fractional.
What do you mean by the length can be
Like
fractional?
n over 1 has
Well, I mean, if you want here, put this as the floor. You know, I'm just trying to give you something where this has a tremendous number of terms in it. So there's a lot more things there. And so just because one number is larger than another doesn't mean it has more gaps. So let's try to do an example and see if this clarifies. So let's find all m in 2 to the n plus 1 with a gap of size g starting at index I. And how large can I be? What's the largest I could be if we want to have a gap of length g? No, g minus 1. So remember, the possible indices are 0, 1, 2, 3, all the way up to n. Well, where can I be? So here is index 0. Here's index 1. Here's index 2, dot, 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 dot. Here's index I. Here's index n minus 1. Here's index n. And we know we have index n. We know that that's one of the summits. What's the largest I we can take and have a gap of size g that starts at I? N minus I?
minus 1 minus I.
Nope. We want a gap of length g starting at I. So how large can I be? Give me a value of I that's too large to have a gap of length g starting at it. Not I plus g. Well, I asked an easier question right now. Give me a value of I that's just too large for there to be a gap of length g starting at I. N, right? Because if we started with I over here, it's too far. If g equals 1, where could we start? N minus 1. If g equals 2, where could we start? Well, we wouldn't be able to start at n minus 1. So in general, where can we start? N minus g. So we can't start I beyond n minus g. Okay. And so now if we just put in a few more things, here is I plus g. And so we would want both of these to be taken. And what about all the stuff in between? What must be true about all of those? If we want to have a gap of length g starting at I, what must be true about all of these? Not that there's 0, that we don't take them. So we can't take any of the stuff in between. So we have 2 to the n, that's forced on us. We have 2 to the I and 2 to the I plus g, but never 2 to the g, 2 to the j, if I is less than j is less than I plus g. So if we want to have a gap of length g starting at I, it has to end at I plus g, right? It starts at I, it ends at I plus g.
Are we assuming g always be non-zero?
Yes, because for this stuff, we know we can't have a gap of length 0. That would mean we'd have to have multiple copies of the same thing. For other things, if we're doing things base 10, you could have g equals 0. So we can be explicit and say g greater than or equal to 1. So is everybody clear that the structure has to be like this? Now, over here, here is I plus g plus 1. Here is I minus 1. Everything in here is free. and everything in here is free. Right? It doesn't matter whether or not I take summons between 0 and I minus 1, or if I don't take them. It's not going to affect whether or not I have a gap of length g starting at I and ending at I plus g. So those choices are completely free. Similarly, when I go from I plus g plus 1 and onward, I can take or not take. It's not going to affect whether or not I have a gap of length g between I and I plus g. But I have to be careful. I have to remember that I have to choose 2 to the n. So now, how many such numbers? The number of choices with a gap of length g from index I to I plus g in 2 to the n plus 1 is the following. So how many choices do I have to fill in the first part? How many indices are there? And for each index, how many choices are there? So I want to figure out how many numbers m are there. So I need to just count how many legal decompositions, how many legal binary expansions are there where I choose I choose I plus g, and I don't choose anything between I and I plus g, and I choose n. Those 3 indices I have to choose. I can't choose any index between I and I plus g. And then all the other indices I'm free to choose or not choose. And I just need to count how many ways can I do this. And that will be all of the integers in the interval 2 to the n plus 1 that have a gap of length g that starts at I. So how many ways can I choose whether or not I have indices or not from 0 to I minus 1? So how many choices do I have for index 0? 2. How many do I have for index 1? So how many ways do I have to choose both index 0 and index 1? 4. How many ways do I have to choose index 1, 2, and 3? 8. So how many ways will I have to choose the indices from 0 to I minus 1? 2 to the I. So we have 2 to the I from index 0 to I minus 1. How many ways do I have to choose indices from I plus g plus 1 to n minus I? Yeah, now you have to worry about the plus 1s and the minus 1s. So when I went from
That second bracket from I plus g plus 1.
I plus g plus 1 to n minus 1, how many ways can I choose the indices?
Plus g, or n plus I plus g.
No. Well, let's think. How did we get how many indices there are from I minus 1 to 0? What did we do? We subtracted 0 from I minus 1 and then added 1. You know, how many integers are there from 3 to 5 inclusive? 3. But if you do 5 minus 3, you get 2. You have to remember to add 1. How many integers are there from 2 to 10? There's 9. 10 minus 2 is 8, plus 1 is 9. So if I want to count how many indices do I have here, it's n minus 1 minus I plus g plus 1. And I have to add 1 to that. So it's going to be 2 to the n minus 1 minus I plus g plus 1 plus 1 from index I plus g plus 1 to n minus 1. So that's 2 to the I. And now we have n minus 1 minus I minus g. All right, so we're going to get an n minus I minus g. We have a minus 1. We have a minus 1 is a minus 2 plus 1, so it's going to be minus 1. So it's going to be 2 to the negative g, 2 to the n minus 1. Yes? How many numbers are there in 2 to the n to 2 to the n minus 1? So the number of m in the interval 2 to the n to 2 to the n plus 1. How many numbers are in that interval? I'm sorry?
Depends on your choice of n.
Sure. So give me the answer as a function of n.
So n plus 1 minus 2n plus 1.
Say it again.
2n plus 2 to the n plus 1 minus 2 to the n minus 1. Just looking for the number of integers in that interval.
Mm-hmm. So the question is, do you have that minus 1 or not? So for example, if we go from 4 to 8 like this, that's going to be 7 minus 4 plus 1 is 4. It's just going to be 2 to the n plus 1 minus 2 to the n, which is 2 to the n. So there are 2 to the n integers between 2 to the n and 2 to the n plus 1. If you're going from 4 to 8, we've got 4. If you're going from 8 to 16, we have 8. This is why, it's really nice that we're not including the right endpoint. So we have 2 to the n integers. Now, we want to find how many have a gap of length g. So let's let xij equal the number of m in the interval 2 to the n plus 1. Put an n there. With a gap of length g starting at I. Okay. And we know that this is equal to 2 to the negative g, 2 to the n minus 1. So this is giving us a gap of length g starting at I. How would I figure out how many integers have a gap of length g anywhere? This is going to count how many gaps of length g I have starting at a specific place. So how many gaps of length g are there among all the integers? We just found a formula for how many integers have a gap of length g that start at I. So what are the possible starting values for I? 0 through, not through n, not through g. So this is, we know I can't be larger than n minus g. So we would sum I goes from 0 to n minus g, and then we would record how many times do we have a gap of length g starting at I. So we would just have to execute the sum. Is this clear? If this is not clear, please speak up. Does this make sense? So what's nice is, notice that the number of times we have a gap of length g starting at I is independent of I. It's just depending on g. So this is going to be a sum. I goes from 0 to n minus g of 2 to the negative g, 2 to the n minus 1. Well, I can just pull the 2 to the negative g, 2 to the n minus 1 outside, and then I have a sum. I goes from 0 to n minus g. What does that sum equal? So what would that sum equal? Nope, almost.
It might be plus one.
I'm adding 1 n minus g plus 1 times. So what would the sum equal? N minus g plus 1. And that will be the number of gaps of length g that I have among all of my numbers. So it's possible that some numbers could contribute multiple gaps of length g. Whenever you do counting, the biggest danger is double counting. You've got to make sure you don't count anything multiple times. So for each number, when I look at its decomposition, it could have multiple gaps that are the same. When I looked at the number here, I had for the gaps 2, 1, 1, 3, 1, I had gaps of length 1 3 times. So this number contributed 3 gaps of length 1. But they all had different starting points. One of them started going from index 2 to 3. One of them started from index 3 to 4. And so I never counted the same gap multiple times. And so each number has a sequence of gaps. And I can calculate how often do I have gaps of length 1, of length 2, of length 3, of length 4. And now I can ask what fraction of all the gaps are length 1, what fraction of all the gaps are length 2, what fraction of all the gaps are length 3. So now, question. What fraction of all the gaps from integers in the interval 2 to the n, 2 to the n plus 1 are of length g? So the first thing we need to do is, what is the total number of gaps? We know how many gaps there are of length g, right? So what do we need to do? So for each g, we know how many gaps there are of length g. Well, can you have a gap of length n? What's the largest gap you can have? Is n minus 1.
Okay, so between 0 and minus 1. That's
Not the product, it's the sum.
sum.
So we sum, g goes from 0 to n minus 1, the number of gaps of length g. And that will be the total number of gaps. We know how many gaps there are. So now we have to sum, g goes from 0 to n minus 1. And what did we just get a moment ago? We had it was 2 to the minus g, 2 to the n minus 1, n minus g plus 1. So when we look at this, we have a sum, g goes from 0 to n minus 1, 2 to the negative g, 2 to the n minus 1 times n plus 1, minus the sum, g goes from 0 to n minus 1, 2 to the negative g, 2 to the n minus 1 times g. So I'm writing it like this because the two sums need to be handled a little bit differently. One of them I claim is easier to handle than the others. So it would be the first one. So let's analyze the first one. And it doesn't want to let me paste it to the next page. I'll try one more time and then I will give up. All right. Old-fashioned. So we have the sum, g goes from 0 to n minus 1, 2 to the negative g, 2 to the n minus 1, and there was an n plus 1. And then the other one was the sum, g goes from 0 to n minus 1, 2 to the negative g, 2 to the n minus 1 times g. That had a negative sign in front of it. All right. So let's look at the first one. Well, for the first one, I can pull out the 2 to the n minus 1 and the n plus 1. And then I have a sum. G goes from 0 to n minus 1, 2 to the negative g. What does this look like? Do you recognize this? Let me just make sure I'm still yes. So have we seen any sums like this before in our career? Yes, what sum is it? It's a very famous, important sum. So sometimes it's all about pattern recognition. Let me try to rewrite it. G goes from 0 to n minus 1 of 1/2 to the g. If I write it like this, is it clearer what sum this is, what kind of sum this is? I'm sorry? Well, the sum is going to converge, but this sum has a name. This is a geometric, right? What does the ratio equal? 1/2. So you should hopefully be able to recognize that this is a geometric series. R equals 1/2. And so we can use the finite geometric series formula. So if you let Sk equal 1 plus r squared plus ... plus r to the k, if I multiply by r, I get r plus r squared plus ... plus r to the k plus r to the k plus 1. And now if I subtract, I get 1 minus r times sk equals 1 minus r to the k plus 1. So sk is just 1 minus r to the k plus 1 over 1 minus r. So we can use that to evaluate this. So this piece is just going to be 2 to the n minus 1, n plus 1. And now we're using the finite geometric series formula. What would k equal if we want to use this, and what would r equal? So what would k equal and what would r equal if we want to apply this to our sum? N minus 1 would be k, and r would be 1/2. And so we'd get, it's 2 to the n minus 1, n plus 1, and then we would get 1 minus 1/2 to the n over 1 minus 1/2. So 1 minus 1/2 is just 1/2. I can pull that out. That's going to hit the 2 to the n minus 1. That's going to give me a 2 to the n, n plus 1, 1 minus 1/2 to the n. When n is really, really, really large, does the 1/2 to the n matter? No. So this is approximately 2 to the n, n plus 1, if n is large. This is the equivalent of telling Elon Musk, we just found an accounting error, here's another $100, right? When n is tremendous, 1/2 to the n is so small relative to 1, just ignore it. Now we have to deal with the other piece. And so now we have to deal with the sum. G goes from 0 to n minus 1. We have it was 2 to the negative g. Yes. And then it was 2 to the n minus 1 times g. So this is, of course, just going to be 2 to the n minus 1. The sum g goes from 0 to n minus 1 of g 1/2 to the g. And we know that 1 plus r squared plus ... plus r to the k is 1 minus r to the k plus 1 over 1 minus r. So a lot of times, the question is, what's going to make the algebra a little bit nicer? So I could do 1 plus r plus dot 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 plus r to the n minus 1 is 1 minus r to the n over 1 minus r. Have we done differentiating identities yet? Did we do that when we talked about moments? Okay. I'm going to take the derivative of both sides with respect to r and then multiply by r. If I take the derivative of 1 with respect to r, what do I get? I get a shift. I'm going to get a shift division thing. So let's do it very carefully. The derivative of 1 is going to be what? 0. The derivative of r is going to be what? And then I multiply by r, so I'm going to get r. So I'm going to get 0 plus 1 times r. What's the derivative of r squared? 2r. I multiply by r, I'm going to get 2r squared. All the way up to the last piece, which is r to the n minus 1. What do I get when I differentiate r to the n minus 1? N minus 1 r to the n minus 2. I multiply by r, I'm going to get n minus 1 times r to the n minus 1. And this is just d by dr times r of 1 minus r to the n over 1 minus r. So this is called differentiating identities. And so once we have one inequality or equality, we can generate more. If we wanted to sum g squared, we would just take another derivative. If we wanted to sum g cubed times 1/2 to the g, we'd take another derivative. And so if I want to evaluate the sum of g 1/2 to the g, I now take this, let r equal 1/2. And then I can substitute that into here. So I would have to differentiate 1 minus r to the n over 1 minus r. How would we do that? Quotient rule. So we can now use the quotient rule. Now, one thing that you can notice is it's r d by dr. I can write this as 1 over 1 minus r minus r to the n over 1 minus r. When I write it like that, I don't really think this r to the n over 1 minus r is going to matter. Because when n is very, very large, this term is going to have an extra factor of r to the n. And so when I differentiate and do all the stuff, everything is going to have at least an r to the n or an r to the n minus 1. And then when I put it in 1/2, it's going to be so much smaller than this piece over here that I think I can basically just ignore this. And this will give me the main term. So for Monday, you should try to put in the details, especially if this is the chapter that you're writing, is put in the details to finish up this calculation to count the total number of gaps we have. And again, you're going to have a main term and you're going to have an error term. If you have something that's tremendously large, a small error doesn't really make much of a difference. Let me stop here.